everybody. Hello, everybody. So just to reduce confusion, I was just reading on the agenda that it's actually the World Cafe that I'm supposed to talk about, but this is a case study that I will talk about. So, you know, once I'm through my 500 slides and there's time before the dinner, maybe we can answer some of those questions in there as well. Anyway, my name is Gilbert Meyer-Gauen. I'm the Director of Asset Management for National Oilwell Varco. In case you haven't heard about us, which is probably a good chance, I will start with a company introduction, and this is the further content of my talk. I will tell you a little bit about our digital cloud infrastructure and edge infrastructure. I will show you some pictures of the edge devices that we use and tell you a little bit about the software that runs on it. And then we'll go into two case studies that are hopefully interesting for you. And these case studies are focused on legacy equipment that we have in our facilities. One is low-frequency data, which is the first one, and the second one is high-frequency data, actually real vibration analog data that we use to make all kinds of decisions on an equipment. And if there's time, I want to give you a couple of suggestions. If you just want to start in this effort, I will tell you a little bit how we started, give you a couple of ideas, and tell you a little bit of the problems that we faced during our digital transformation that started 4 years ago. So this is a little bit about our company, really not a lot of interesting stuff. Interesting is the stock ticker, NOV. Internally, some of our customers call us no other vendor. Internally, we call it Norwegians on vacation because we do have a lot of Norwegians. And you know, if you try, hopefully there's no Norwegian here in the audience, but if you try to reach them during the summer, it's hard because they are in the outdoors. The thing I want to focus on is really this 181 number down there. We have 181 manufacturing locations worldwide. So this is what the case study will be about. We started about 4 years ago our digital transformation effort. And like Jeff mentioned, the customer was driving that decision. They were coming to us and they wanted to have more insight and more data from the machines that they bought from us. And at that point, we started to realize we really have to change as a company. And you may have heard this topic before, but never really believed that this is really happening. But we as manufacturers really turn more and more into software companies, and this is really true. This happened in our case. So we started to create a group that started with 4 people, and over time it's now over 150 or 200 people. And the reason why we did this is because we had to. The customer wanted to have data from their machine that is in hard-to-reach locations, so we had to develop an edge presence. We have to have devices on the machine that can capture the data, and if there is no internet connectivity, buffer the data. And then at the same time, the customer also wants to have access to their data, so we have to somehow get that data from these edge devices into our cloud so we can give it to the customer. And then finally, the customer also wants us as an OEM to give them insight into their data and maybe suggestions on where they are with their equipment, what's the lifetime, and so on. And so we also have a portal that is basically a fast development platform for visualization of that data. So these are all the pieces that make our digital platform at NOV. Now, the oil and gas drilling industry, this is where we are really mainly working in. We are designing equipment that is used in oil and gas, we are servicing it, and we are also maintaining it. So the problem with a lot of our equipment is that it's really in the middle of nowhere. It's sometimes in areas where you don't even have internet connectivity. So from the get-go, the edge presence to us was very, very important. And it was also important to us to be able to scale it. So you know, we didn't want to just focus on one particular edge device. We wanted to be able to run our edge software or our edge firmware on any type of device, from a Raspberry Pi to a large industrial server. And this is what we created over the last 2 years. It's basically a hardware-agnostic software stack. It can run in very small units like the one above. This is a Moxa unit that costs about $200. And then you can go down to a larger unit that has a little bit more processing power, to a really larger device like I think that's a Dell box down there that could potentially run data from all the machines at an entire drilling rig. So that was a very big effort for us to build a software stack that can do it. It runs on industrial Linux, of course, for safety reasons. We don't use Microsoft Windows for that. For various reasons, security is a huge item in all of this. When you have thousands of these units in the field, you want to make sure that nobody can get into or listen to the data. So we use all the typical methods to protect the data that we send from the edge device to the cloud. And this is constantly changing. I mean, there's no week where this team that works on this is not investigating other options and more secure methods. And one big deal is when you have edge devices in the field, you have to be able to remotely manage them. And we are also able to do this. So how do we do all of this? Very simple. It's all based on containers. So you probably have heard Docker containers. These are small little virtual machines where we run small little microservices on it. And it's actually pretty cool how this works. You can remotely start and stop these containers, and this way even basically provision a device if it's already in the field. We also have health services running on these devices to tell us whether a device is up and running or disconnected, how it's doing, what the CPU processor power is. So we can also remotely make decisions about the health of these devices. Of course, because it's containerized, we can add all kinds of services to a rollout. So for instance, let's say we have a customer in the middle of the ocean. And when they move the drilling rig, they turn their satellite connection off, which is actually a typical situation. When they move a drilling rig, they turn off the satellite, and then they do all of their maintenance. So worst case scenario for us, how do we support our software in such a case? Well, we have onboard storage on these edge devices. You know, a database stores all the data that comes in. And the edge device also runs the maintenance system, all on the edge. So this is how we solve that situation. Now to do this, of course, you have to be really inventive in how you do this, how effective your microservices are. Don't try to run anything heavy on it. .NET Core may not work. You may have to go to other technologies that are out there. There's a whole bunch of open source solutions out there that allow you to reduce the footprint and improve the performance of these little services. And then the last thing I want to talk about, these edge devices, we always thought of them as really a one-box do-all. So you can really go to pretty much any machine with these edge devices and plug the data from the machine because it supports all kinds of industrial communication protocols. So we have a roadmap of 42 protocols that we want to support. Right now we are at 20. So these machines can read CAN bus, OPC UA, we.CONECT, Modbus over TCP, just to name a few. We also support some oil and gas specific protocols. So the idea is that with the scalability of these devices, depending on how many readings the customer want to read, and these protocols, we should be able to really pull the data from pretty much anything. And if it's not there, our team will develop another microservice to pull the data in. And then, of course, the last thing is, now this we haven't done yet, but we know how to do it, is a closed loop feedback to the control system to not only do data capture on the edge device, but also send information back to the control system, which of course is kind of like the holy grail of this all. I mean, if you do prescriptive maintenance, which is something where the system itself fixes itself, you could potentially do this if you have a closed loop feedback to the control system. Yeah. All right, so as a company, internally, this was a lot about the products that we sell, but internally we are using the same technology, and here's why. This is a picture from, I think that was a press that we bought a company last year, and the reason why we want to do this internally, look at this, 1909, that's the manufacturing date of that machine. So obviously, we do have a lot of older machines, and to us, the maintenance of these machines is becoming a real problem. And using these edge technologies and all the other stuff, the condition monitoring, tremendously helps us doing this also inside of our own manufacturing facilities. And this is what I want to talk for the rest of, maybe 15 minutes or so. So I have two case studies. As I was saying, one is low frequency data, which is the induction heating cabinet that you see here. And then the second one will be high frequency data. So to give you a little bit of idea, this is a so-called induction heating cabinet. It's connected to an induction welder, and it regulates the temperature of the induction welder. The problem is, the problem at this particular facility is you see a lot of tubes there. So cold water comes in, transformer heats it up, and then the water gets out. The problem is the water quality at this facility is incredibly bad. These tubes clog up, and as a result, the transformer burns out at one point. Transformer cost $40,000 each. We had 2 instances in 2017 and 18. So $80,000 excluding the ordering time and the lead time to get the new transformer, and so it's a big headache. The solution was, why not simply monitoring the inbound and outbound pressure, calculating the pressure differential, and then setting a threshold. When the pressure gets too low, then trigger a work order to replace or clean these pipes. Obviously, the value proposition is tremendous. You would automate the entire process. Your maintenance team would not have to clean these tubes every 30 days, only to find, oh, it's still good, let's do it the next 30 days. So that part alone financed it by itself. So what was our solution? And this is what you see in a lot of cases. There is really no easy button for this when you go into older equipment and into legacy. You have to think outside of the box. There's a different solution for every problem, and every solution may be looking slightly different. So the way we did this is we put our medium Moxa device in there. We have a PLC underneath from Varco, which connects to the pressure sensors, the temperature sensors, and the power sensors. So very simple. You have sensors. Sensors are connected to a data acquisition device, which is a PLC. And now the PLC sends the data to the edge device. The edge device sends the data to the cloud. Cost price, if you're interested, about $6 grand for one machine. I think just by saving one maintenance cycle, you would have that money already in. And this is the visualization. Again, because of our software stack, we can run these Grafana dashboards on the edge device itself. So we have screens right at the induction heating cabinet, and people don't even have to go to the cloud to get the data. They can see almost real-life data right from the edge device. And this is one big reason why we invest so much time and money into edge devices, because we want to make this reliable. What if your internet connection goes down? And it's usually Murphy's Law. It's in the middle of a problem on an equipment. If you try to get to the cloud, you can't get to the cloud. This is a problem. By putting everything closer to the edge, you just increase your reliability. So real-time data too. Usually, although it depends on your internet connection, there is some latency in sending stuff to the cloud and getting it back. It may just be 2 or 3 seconds, but imagine if you have a scenario where something critical happens. 3 seconds can already make a difference. Case in point, this is a real life example from our facility, from a slightly different equipment. I think it was a welder that is oil-cooled, and it has water pipes going through the oil bin to cool down the oil. So for whatever reason, that water pipe had leaks in it. And now the water was getting into the oil. And the oil was getting into the water. So now we not only had a completely messed up oil bin that had to be cleaned, we also had oil in the water reservoir because these cooling cycles are closed. So a solution in this case could have been that the edge device would have shut down the machine immediately if it would have recognized water in the oil bin. And there are sensors that can do this. There are moisture sensors that are very, very sensitive. So we are working on a scenario where we can put moisture sensors at different areas and immediately at least raise an alarm for the operator when it detects moisture so that the operator can turn off the entire system and we no longer have this trickle effect. So speed can really matter in these cases. Not everything has to be in the cloud. Sometimes it makes more sense to move it closer to the machine, and this is one example here. So what you see on this slide is on the upper area, you see the pressure profiles. The green is the inbound water pressure, the yellow is the outbound, and then the blue line is a calculated value, which is the pressure differential, right? And as you see, it's at 37 psi. Now, when we started this at the beginning of last year, it was at 39 psi. So it gets slightly lower over time, but it still hasn't reached what is our threshold, which is 30 psi. So as soon as it reaches 30 psi, our system will generate a work order that is being dispatched to the maintenance crew to change the pipes. And this is an example of this work order. So again, everything is automated. Nobody has to go out there every 30 days. It's not predictive, but it's a good way of saving you a significant amount of money, at least on maintenance cost. Yeah. All right, now to the one that uses high-frequency data. A lot of our equipment is rotary equipment, top drives, drawworks, and pumps. So vibration for us as a company that manufactures products in this area is incredibly important. And by vibration, there are two different things that you have to know. One of all is usually when you buy vibration products, they just give you a single value, which is called RMS, which is just a single value for the overall vibration on your equipment. If you have complex machines, this is not going to help you because you don't know where the vibration actually occurs. You just get an average value, and by using that, you will never ever be able to really pinpoint what component is really at problems here. So to be able to do this, you have to look at the analog wavelength data and do what is called a frequency analysis on it, which means you have to find these areas in your frequency that represent a particular component. So, case in point, this is what we did here. So this Rosler is basically a blast turbine. It has two impellers that are kind of like angled at each other. The impeller spins at about 4,000 RPM and throws small little particles at the drill pipe to strip off the coating. Obviously under high heat, incredibly destructive environment. The problem is these impellers wear out and they have to be replaced. How do we know so far whether an impeller is good? Well, for that you have to turn off the machine, let it cool down, open it up, takes 3 maintenance technicians to do it, and do a visual inspection. Then it takes another 3 hours to heat it up again. So imagine in a 24/7 environment with no redundancy, you take a machine like this down for 8 hours, it's a huge cost. And I'm talking about loss of revenue in the 6 figures per hour in this particular case. So the solution to this particular problem was to install accelerometers at these equipments and measure the vibration, with the idea, okay, when these blades wear off, the vibration on these impellers increases, and now all we have to do is monitor the vibration. And this is what we did here. Whenever you work with high-frequency data, it gets more expensive, unfortunately. And as you can see, 11K, and the reason is really that the data acquisition device that you can use, you can no longer use these regular PLCs. You have to go much more powerful. And that's what we did in this solution. So this is down there at the very bottom, that's the data acquisition device. It's from National Instruments. It's called CRIO and costs $5 grand, that thing alone. Vibration data, again, you need a lot more bus speed, a lot more horsepower to handle this analog wavelengths data. I mean, we are talking about 20,000 readings per second per axis, you know? So you have one accelerometer, that's like 30,000 readings per second. Now, we don't do it at that rate. We use 6,500 up to 10,000, but you know, we also have solutions where they use 20,000 hertz. But for this, you cannot use the CRIO any longer. You have to go to the crazy Danes. They have a company called Brüel and Kjær, where the device costs like, I don't even know, 9 or 10 grand. So this is the data acquisition device. The black one is the edge device. And again, you know, it's no longer a small MOXA. It's a large edge device, because with increased readings, you need more horsepower on these edge devices. And this is our solution to do this. All right, now Grafana, of course, has problems showing analog wavelengths data. So in Grafana, we still show RMS data, which is this overall vibration value. But we also could provide real-time run hours on that Rossler, which was really helpful. They couldn't even tell us how long they usually ran these impellers. So just the run hours on this from the data is already a big gain for them. And this graph, I'm not going into really details in it, but it's very interesting. So the upper level shows the signature RMS data before and after the impeller change. And this is why I was mentioning RMS really for complex heavy machines doesn't give you any information. So before the signature, before the impeller change, look at the RMS signature. It looks almost identical to the one after. In fact, I would make the point that the one after has much more spikes and could actually look much more erratic than the one before the impeller change. So this is just the overall vibration. Obviously, not very valuable. So what we have to do is we have to take the analog wavelength data and run a frequency analysis on it. And this is what you see now there. So the impeller is at the 50 hertz range down there. And this is where you now see the difference between before the impeller change and after. So obviously, this is the value we want to monitor over time. And by doing this frequency analysis, we were lucky enough to start this effort before we changed the impeller. So now we have a good baseline. Always remember, this is something very important to have a baseline if you really want to do this. So do it before maintenance, and then you have a baseline where it shouldn't be, and then you should see after maintenance this baseline drop or go higher, depending on what you're looking at, and then over time go back to the old baseline before the change. So this is shown in this graph. I told you it has two impellers, so these are graphs of these frequency analysis at 50 hertz for both impellers. And don't worry about the green one, that's the motor bearing, but look at the yellow one. So down there at the very end, that's when we changed the impeller. And the frequency was at that point pretty high. After the impeller change, you see the yellow go down to a very low level. And now, since last year, we are monitoring it over time. And as you can see, obviously, the frequency vibration goes up slowly, but we haven't still reached the level of the vibration that was when we changed the impeller. And because it's the first time we did it, we still do visual analysis to really make sure that what we are measuring represents the actual case. And this is what I will show you. These red dotted lines are the next 4 slides from left to right. So obviously, the first slide will show you a picture of these impellers before we changed it. And then the next line will show it after 370 hours, 720, and I think these are from this year, just fresh off the press, after 1,250 hours or so. All right, so this is how the impeller looked before the change. Obviously, pretty concerning. Even the disc that holds these pedals is pretty much worn out. Now, from a maintenance perspective, that gives me a heart attack, because you should never run your equipment up to that point, right? That's another thing that we hopefully can get away with, no longer changing it when it already is worn out, because you ultimately cause failure and problems and other things to your machine when you do this. Okay, now this is after the impeller change and 325 run hours. Obviously, there is wear, but it's pretty insignificant. And this is actually what we see in our vibration as well. So this is after 740 run hours. You can already see more wear on it. So we are still good. This looks like it's working. And this is now fresh off the press, and you can now really start seeing the metal peeling off. So obviously, the vibration data really represents what we see in visual inspections. And now what we are doing, we are just waiting until we get somehow close to that yellow line, and then work with the maintenance crew to have the impellers replaced. All right, so this 2 quick case studies. Each one is different. Remember, high-frequency data takes a lot more effort. Low-frequency data is usually straightforward. So if you have ever wondered how to start, here are some, I think, decent ideas. The Bosch XDK is actually a really cool piece of equipment. It's a sensor that has all kinds of stuff in it. It's cheap, $180, $200. It has processing on the unit. It does accelerometers. If you just want to play around with it, this is a good place to start. Actually, a lot of plants, it was just meant to be a development tool, right? But a lot of plants are using these in real-life environments. Raspberry Pi, especially Raspberry Pi 4, pretty small little powerful unit, perfect for this type of stuff, especially if you think of Docker containers and containerizing all your stuff. This is really where the direction goes on the edge. We just had meetings with Vargo, so now Vargo PLC is actually also able to run Docker containers. And for us, this is a huge deal, because remember, our firmware is built on Docker containers. If we can just run our stuff on these Vargo PLCs, we cut out one device, hence making things cheaper, more scalable, and having to have smaller JBoxes and all that stuff. And from a software side, we do have commercial partners, but we also do like open source products. And these are some of the open source products that we are using or used to use. Like Node-RED is actually a really cool product. It's an orchestration tool. It's drag and drop. That would be a good starting point for you to figure out what to do with the data if you want to start in this effort. Because it's drag and drop, you can say, hey, put it to an Excel spreadsheet, move it there, without you having to write code to do this. Node-RED runs perfectly in a Docker container, by the way. Grafana for dashboarding, of course, and we are also looking at Timescale DB right now as our time series database. All right, finally, challenges. Of course, how do we measure edge device health? I can tell you we had cases where people would unplug these devices. That's a real problem, so we started to realize we have to do a lot of logging on the device to make sure that we can troubleshoot issues that arise later. What caused the downtime on the device? It can be that you had a bug in your software, or that you had a memory leak, or that the customer simply unplugged it. So remember that if it's in the field, you cannot simply go downstairs and look at it. So you somehow have to have solutions to this. Connectivity, somebody was asking. Very good question. Connectivity, there are all kinds of solutions. You can have dual SIMs nowadays. We use that sometimes, that have Verizon and AT&T, because somewhere in the middle of Texas, Verizon works better than AT&T. There are also solutions with a global SIM that searches the vendor locally. We also sometimes don't have any connectivity. So if you don't have it, make sure that you store your data in a database on the device, and then have it backfill once the device comes back online. PLC manageability, that's a huge area. I told you this is the closed loop feedback. We are still working on this, and the baselines. All right. We still have time before dinner, so if you guys also want to ask questions about some of these questions here, edge versus cloud, who will win, what is fog computing, feel free to ask questions. So that's pretty much it. Thank you very much.